Hello everyone. This is the second in my series of decomposing rational expressions into partial fractions. The difference this time is that we have a linear factor which appears twice in our denominator rather than being two different linear factors. Now there's a very small difference that we need to apply for this one. Like last time, we'll split this into two partial fractions. There's two linear factors, there'll need to be two linear fractions. But what you might think, oh well, x plus 2 appears twice, so we'll put x plus 2 as the linear factor. The trouble with this is that these two things won't give, well, they're not unique. So the trick this time is our first one is x plus 2 squared, and the next denominator is x plus 2. When you have repeated linear factors, you have to treat them like this. This time it's squared, so we'll have to have x plus 2 squared on our first partial fraction and x plus 2 to the power 1 on our next partial fraction. From here on in, we treat things in exactly the same way. So we're going to need to make a common denominator which looks like this. Now don't be tempted to multiply the two together, otherwise you'll end up with x plus 3 cubed, which is too big. So our common denominator, when we add these, has to look like what we started with, x plus 2 squared. We already have x plus 2 squared. The term from our first fraction is just a in the numerator. The second one, well, we would have to have multiplied both top and bottom of this by x plus 2 in order to make the denominator of this one become x plus 2 squared. Now we have this, it's what we want. 4x plus 5 would be the same as a plus b times x plus 2. So we'll write that down. 4x plus 5, we have a plus b times x plus 2. Don't be tempted to multiply out. I actually like the fact that those things are going to be there like that. Now, again, x is the pronumeral. We need to evaluate the letters a and b that make this equal to this. So the smart choice is to pick a value for x that makes this part disappear. So let's have x equal to negative 2. When we substitute, we have to substitute on both sides. So 4 times negative 2 plus 5 would equal a. And then this bit is gone because negative 2 plus 2 is 0. So we have here, that's negative 8. Negative 8 plus 5, that's negative 3 equals a. So we know a. Now we have to evaluate b. Well, for this one, there's no obvious choice for x. So we might as well make an easy one. We don't want to put a value for x the same where this disappears. We actually want this to be non-zero this time, so b remains. So we can pick anything we like. Letting x equals 0 would make our life a bit easier. So the left-hand side, 4 times nothing, clearly is nothing, plus 5. Over here we already know a is negative 3, so we'll reuse that, plus b. Now 0 plus 2 is 2, so that's plus 2b. Solving, we'll have 8 equals 2b. It looks like b equals 4 in this case. So rewriting our solution then, we started with 4x plus 5 over x plus 2 squared. We thought that a equaled negative 3, and that had a x plus 2 squared in the denominator. We thought that b equaled 4, and that had the linear factor x plus 2. So this is the decomposition of this rational expression into two partial fractions. The trick again this time, because we had a linear factor that was repeated, we had to have one of our fractions with the squared power and one to the first power. If this had been a cubed, then we would have three of these things when we set the question up. We would have had a cubed, a squared, and a linear power. And so it would go for higher powers as well. Well, that's enough for this little video. We'll do one in another couple just to keep practicing these.